Okay, so we are going to start off with our first lesson for Unit 3, which is about lines and planes using vector representations and something called parametric equations, scalar equations, symmetric equations. So depending on what we're going to be working with, there's several different ways of representing the equations of lines and planes in 2D and in 3D, particularly when we're talking about planes. So our learning goal, as I just said, by the end of class, I will be able to determine the scalar, vector, and parametric equations of a line in 2 space. That'll be part 1, and part 2 of the video will be in 3 space. Okay, so we're going to start with something that is actually quite familiar, and that is the standard form of the equation of a line. So the line that's here, we have x minus 2y plus 5 equals 0. So standard form, since the x is positive, there's no fractions, and everything is on one side of the equation. I'm actually going to change this equation to make our life a little bit easier to be, so I'm going to change that. I'm going to change it to be x minus 2y plus 10 equals 0. Now the reason that I'm making that change is so that when I rearrange to y equals mx plus b, so I have x plus 10 equals 2y, I have 1 over 2 x plus 5 equals y. This just makes it a little bit easier to generate the graph for our line. So I'm going to plot that. So I'm at 5. My slope is 1 over 2. So I know I have a point here, 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 so on and so forth. So we're just following rise over run, just like we're back in grade 9. And then I am going to add a line okay. And because it's a line, I am going to add arrows on the ends. Okay, so nothing new here. The next thing I'm going to write, I'm actually going to write out the vector equation. So it's not a format you're familiar with. So the vector equation of this line is r equals 0, 5 plus t multiplied by 2, 1. And you're probably like, where is this coming from? So this here represents one of the infinite possibilities for the equation of y equals 1/2 x plus 5. So if we sort of analyze the numbers in y equals 1/2 x plus 5, the 1 and the 2 appear right here. So we call it a slope when we have standard form. When we're talking about the vector form of the equation, we call this the direction vector. So that it kind of controls the slant of the line. So we have to have a direction vector in order to have the equation of a vector. Just like in order to have the equation of a line, we have to have the slope. To get the y-intercept, we had to know another point on the line. So in this example, this 0, 5, it is the y-intercept, but I'm going to call it the position vector. Okay, so now I'm going to actually plot these two vectors. So vector 0, 5 would be coming from the origin up to that line. Then the direction vector, which is at 2, 1, would be right here. So in your textbook, they call this R0 for the position, and they're going to call this M for the direction vector. So basically what we are doing with that variable t, if I were to pick this point right here, okay, and connect it to the origin, so this would represent r at that particular point. So this r represents a position vector anywhere along the line, because if we look at it, this piece up here, if I look at it, I have vector m once, twice, 3 times. So this here is like having 3m's. So this particular point right here, if I were to figure out where that point is, I know that it's at 6 and 8. And I can figure that out using the equation. Well, I can tell what it is here on the graph. But ultimately, we want to generate vector equations for lines. And in 2D, you're always going to need the same two things. You need a position vector, which is any point on the line, and you need a direction vector. Now, another way that I could write this equation, I'm going to use that point instead. So my equation is r equals 6, 8 plus t, and I could have -2, -1 as my direction vector, because -2, -1, 2, 1, they are collinear. So the direction vectors, as long as they are the same collinear vector, you can use that value in order to figure out a vector equation of a line. This format is always going to apply. And as I said, you will always need a position vector and a direction vector. What makes this unit fun to mark is everybody could actually have a different answer because there's an infinite number of position vectors. Technically, there's also an infinite number of direction vectors, because you might write 6, 8 plus t multiplied by 4 and 2, or 12 and 6. And they are all considered to be correct because they are all multiples of your direction vector. So that's going to be our job when we're figuring out the vector equations of lines in 2D and then ultimately in 3D. So here's a little summary. So vector equation of a line in 2 space. So this is that r naught and the m that I was talking about. So it's the addition of those two vectors. I drew them so that they were tip to tail. This is just putting it in coordinate form. And then r's obviously real numbers for us because we're not working in the imaginary plane. We have a position vector. So that's the net vector that we're looking for. So it's somewhere down that line. Here, the r naught, that is a point, and then the direction vector is equivalent to the slope. Okay, so here's a typical example. I'm actually going to plot a grid here to help me a little bit, because we're just starting to visualize this stuff. Okay, so I'm going to drag this over here. Okay, so write the vector equation for the line through the points A1, 4 and B3, 1. So I'm going to start by plotting those points. So 1, 4, so this is A, and then B is at 3 and 1. Okay. Now really, this question could be a question that was given to you in grade 9, except we wouldn't have called it the vector equation of a line. But back then, you were trained to recognize that you needed the slope and you needed to know what the y-intercept was. For us, we have one less step actually. All we need to know for every single vector equation of a line, we need a position vector, and we need the direction vector. So if I asked you to tell me what the slope of AB was, you would use your formula y2 minus y1 over x2 minus x1. That's basically what we're doing when we're creating a vector AB. So the notation that's often used for the direction vector, we use letter M. It's just a notation. So it's kind of linked to the slope concept. So M, because I drew the arrowhead at B right here, I'm going to start with point B. So I'm going to do 3 subtract 1, and then I'm going to have 1 subtract 4. So that gives me 2 and -3. So if I were to plot that, I need to move down a little bit here so we can see it. So if I were to plot 2 and -3, what do you notice about that line compared to vector AB? Hopefully you're saying it's the exact same thing. Now what if I were to do it in the opposite direction? So this here is vector AB. What if we did BA? Doesn't really change much, except we would have 1 subtract 3 and 4 subtract 1. So we would have -2 and +3. So So now I'm going to plot that point. So -2, +3. Apologize for my lack of straightness, but you see the idea. It's the exact same thing. So now we know the slant of our vector. We need a position vector. You have two to choose from. You have point A and you have point B. So, based on what I've written here, one possible answer would be 1, 4 plus t 2, -3. T is what we call a parameter. So kind of like when you had y equals mx plus b, if you knew what x was, you could figure out what y is. Same thing with t. As long as you know what t is, you can figure out a specific point on that line. So a specific position for that vector that you're going to be looking at. So t is a parameter that can be any integer value. So positive or negative integers that we would have for t. So you can substitute anything in. You could even actually use half. They don't need to be integers. They can be real numbers. So that's one possible answer. Another possible answer could be, so depending on which point you chose to take, so I chose A at 1, 4. I could choose B, which is at 3, 1 plus t. And let's say I had the other direction vector, -2 and 3. Equally 100% correct. Okay, so that is the direction vector, the equation. Now for part B, it wants to know 3 other points on the line. I'm not going to do all 3, but to do a question like that, you're choosing what t is going to equal. So I already know the point 1, 4, and I know the point 3, 1. If you make t equal to 0, you get 1, 4. If you make t equal to 1, you're going to get 3, 1. So I'm going to use this equation right here. So if t is 2, I'm going to have r equals 1, 4 plus 2 multiplied by 2, -3. So when you expand that, you're going to get 1 plus 4 is 5. I'm putting my x's together. And then 4 subtract 6 is -2. So that's one point that we would have. And actually, because it's a point, I should be using round vectors here. If you want to get other points, all you're doing is changing t. So we could make it -1. You can make it 25,000 if you want to. I'm sure there will be one of you, there always is, that's going to do that. But generally, anytime you're looking for a point, you're just changing the parameter. Now the last question is asking, is the point 2, 3 on the line? And it's saying to do it algebraically. All right, so what we're going to do here is we're going to use our equation. So I'm going to sub 2, 3 in for the position vector or the point that we're looking at. Again, I'm going to just use that first equation. Okay, so if it's on the line, it has to be a value of x that we could get. So I'm going to set up an x equation. So I have 2 equals 1 plus 2t, and I have 3 has to equal 4 minus 3t. So now when I isolate, I'm going to get 1 over 2 equals t, and I'm going to get -1 over -3 equals t. So that's actually plus. The fact that these t values are not the same, that point is not on the line. So if I were to look at my vector AB that's joining right now, and if I were to look at the point 2, 3, 2, 3 is right here. Graphically, I can see that it's not on it. But graphing can sometimes be time consuming. This shows it algebraically why it's not on there. Okay, so what I just actually did, I used something called a parametric equation. So a parametric equation, you're taking the vector equation and you're breaking it up into the x and y components, which makes it easier to work with depending on the situation. And you'll notice that the x component is made up of the x component from the position vector, the x component from the direction vector, and the parameter. So they're called parametric equations because they maintain that parameter that we have there. So these are very, very useful for checking to see if points are online, checking to see if lines are the same. There's a bunch of different applications that we'll use for this here. But anytime you're asked about a parametric equation, you're breaking it down into the individual components. So here is a question that could be on the test or anything. So consider the line. So it's given to you in the parametric equation format. Find the coordinates of 2 points on the line. Okay, when I'm looking at that right now, I know right away that one of my points is 3, -5, because I'm going to translate this into a vector equation. So the numbers without the parameter, that's the position vector. And then the t, now I have my direction vector. So the x component of the direction vector is 2, the y component is 4. So that's that equation. So I know right away that 3, -5, I forgot the negative up here, is a point on the line. Another point, if I were to let t equal 1, I would have 3 plus 2 is 5. Oops, I didn't mean to close that. T is equal to 1, so I'm replacing t with 1. I'm going to have 5 and -1. And again, it's a point, so that should be a round bracket. Okay. Now B, so I kind of skipped ahead a little bit, so this is B up here. So what you need to take away from this is that with the parametric equation, you automatically have your position vector and you have your direction vector. Now, the scalar equation of the line. So that means you want to end up with ax plus by plus c equals 0, or the standard form. So I know what my the points are that I have right here. So I'm going to find my slope. So I'm going to have -5 minus -1 over 3 minus 5. I'm using the 2 points that I just generated. So I'm going to have -4 over -2, which equals 2. Y equals 2x plus b. I'm going to pick one of those points to sub in. So I'm going to have -1, 2 multiplied by 5 plus b. So -11 is going to equal b. So the slope-intercept form is y equals mx plus b. So we'll have y equals 2x minus 11. 0 equals 2x minus y minus 11 would be the standard form. Now the last example is D. Determine if it's parallel. So in order to figure out if lines are parallel, we're looking at the direction vectors. So for L1, the direction vector is 2, 4. For L2, the direction vector is 3, 12. If they're parallel in 2 space, these direction vectors are going to have the same reduced value. So I put it down into lowest terms by dividing by the greatest common factor. I have 1, 2, and I have 1, 4. So therefore, they are not parallel. Okay, so that would be the type of question where you are trying to figure out if it's parallel, and it's all based on the direction vector. If they are parallel in 2 space, you have to check to see if the points are unique, because it could be the same line. All right, so that ends the 2 space vector and parametric equations. So hopefully it makes sense. Part 2, we'll look at 3 space.